Yes, you have
I have the number, but we have to see the number of people.
Okay, we hope for it today.
Because it's here, but
Yo, Daniel, Sylvie Servigne.
Como 15.
Perfecto.
Jóvenes y flacos, por favor. Jóvenes y flacos. So we're going to start the second session. It is with great pleasure that we welcome Sylvie Servigne and Jean from Lyon. Today is the Lyon Day. And they will talk about data science and cross-disciplinary aspects for understanding urban data. Thank you very much for coming, and I let you start.
So we are going to present our work, our research work, and for this work we have an approach with the pluridisciplinary people, and we are coming from the LIRIS, Computer Science Laboratory, but we are working with people of the laboratory EVS, Environment, Cities and Society, the social sciences. And we work also because our use case concern energy efficiency of building. So we are working too with researchers coming from a thermal laboratory. So it's really when we merge social sciences and physical sciences, it's really pluridisciplinary approach. So what is our motivation? In fact, we can say that there are a lot of phenomena in environment and in urban cities that are very complex. And now we can't say that only one discipline can answer to these complex difficulties. So we think that it's necessary now to mix people coming from the different disciplines to try to understand the phenomena. The difficulty even to talk together and to understand the others. So we focus first on one problem concerning building energy efficiency, and in this problem, actually, there are a lot of systems to try to manage energy efficiency, and a lot of physical materials and so on the buildings. But in fact, when these buildings are instrumented with these systems, they don't take care of people who are living in these buildings. And it is necessary now to understand systems, monitoring systems, energy systems, and so on, and to understand how users' behaviors, how they use the building, how they use the energy, and to understand the use and the physical systems, and to try to understand and to manage and to optimize these systems and this monitoring. So we are we think very strong, but it is necessary to have a multidisciplinary approach. So computer science, and we focus on databases problematics, and thermal sciences and social sciences to understand social and users' behaviors. What we want to do, we want to analyze a lot of data. And this data can come from a lot of sources. And to understand this data, it is necessary to have the same words to understand what are the words and the model who are being used in the social science, what are the models which are used in thermal science, and what are the models used in computer science. So we want to have shared models and to have a vocabulary that we can share and to understand each other. It's not so easy as we think at the beginning. We have a masses of heterogeneous data to be collected. So there are data coming from sensors, but also we can have data coming from surveys, questions asked to the users and answers of the users. And we can manage also data coming from social networks and so on. Then we want to understand, so to analyze. When we say we, it's for scientifics, it's for science people to understand. It's not for user of the buildings. It's for thermal sciences to understand why the system are used, why the system are good or not, why the system are, if the system are efficient or not. So it's for scientists. We focus on scientist analysis. So we want to cross-analyze. Cross-analyze what? Cross-analyze data which are very different and to understand among time, among space, among whatever, what we can cross and say, oh, it's special, there is something here, the answer of the people, with the physical capture, the sensor, and it's strange. We want this to point this type of things and to merge data that are not merged. So our goal is to make easy the interaction and the correlation detection between data which are correlated. And the second goal is to help the scientists to make them emerge new hypotheses and to understand the phenomena. So, first we focus on data coming from sensors. In building, these sensors can measure humidity, can measure temperature, can measure open door, open windows, and so on. So this data, this measure come from sensors. And we use also surveys. So the user of the building, we ask a question about their feelings and try to merge feelings and data coming from physical sensors. We first focus on sensors and survey, and then not at all social networks. So data coming from surveys and data coming from sensor are very different. When you ask questions to people, you have some answers. When you ask sensor networks, you have measure, and it is not the same. It's not the same format. It is not the same standard. It is not. We can have words, we can have numbers, and so on. So our data are heterogeneous, multi-sources, multimedia, multi-formats. They can be structured because when you have a measure, you can this measure up in database. It's very easy. When you have some question and answers, more or less, it's less easy. So we can have data or data stream. it's not the same. This data may be voluminous. It depends on the type, the time we collected the data. So we can say that we have a big data problem. And the data is very important for us, is multidimensional, because when you want to analyze, you need dimension to analyze. So we can analyze data among time, space, source, and so on. And it's necessary when you want to correlate data to define same dimension, to have same axis to analyze the data. So it's very difficult to have data coming from sensors and to know the whole chain, the whole life cycle of the data. So we decide to have our own platform, and we instrument building with a lot of sensors. So you see there that we have 300 sensors, and this in a real building in our campus. And the major are there: temperature, humidity, CO2, luminosity, opening of door, window. Every 15 minutes there is data, and we also have a survey coming from users, question concerning feelings. So what is the challenge? So you see the building, and some of them were installed the sensors, and we do that. We are computer scientists, but it was up to us to install and have the data, the research in France. And here you have the sensors. So sensors of, let's say, luminosity, CO2, temperatures, and open detection of opening or closing the door. So what is a kind of challenge can be this: to try to validate physical model, the thermal model, taking into account users and uses. In fact, actually, the physical model try to be validated, but only with physical aspects. So in building, in fact, we see that the new system concerning energy efficiency are not so efficient because of users, but it's normal. And we are not robots. What is our methodology? Methodology into two parts. The first one is it's our methodology. We define this. The first one is to design a generic model, which can be used as a generic ontology. And we decide to do this together with thermal scientists and with social scientists. It was very funny. So we made a lot of multidisciplinary meetings. And sometimes we were discussing, and for example, just to understand what is a sensor for thermal scientists and a sensor for us, it was not the same in our minds. And we think that as we are scientists, physical scientists, our minds were the same, and in fact not. In fact not. So we made a lot of meetings to understand what are the words and to say that this concept, what do you understand with this concept? What do you mind with this concept? Try to explain to us, to every people. All right. To define disciplinary entities, a sensor for thermal sciences, a sensor for computer scientists, and a sensor for social scientists. And try to define conceptual models of every discipline, and then to try to have a generic model for our discipline and that we share this model. And we decide to define the concept which can be shared between social and thermal scientists. So what were our targets? A concept of generic sensor. Generic sensor. In generic sensor, it is not so physical sensor, but also, for example, for surveys. Our generic sensor model can manage data coming from surveys. To define the concept of data series. In fact, we need to analyze things, urban things, physical things, human things. When we analyze these phenomena, it depends a lot of time. So you have a series, data series, that we need to define the concept of data series. And to analyze, to make the analysis, we need a multidimensional structure. So to define the axes of each dimension, and this axis can help them to analyze the data. But this structure depends on what the scientists want to analyze. So the structure is not defined at once, it is defined, but what are the scientists interested in? Thermal scientists are interested in this time and space, but in this time, what is the granularity of time? The various level of the dimension. When you have time, you have the timestamp, then you can say minutes, hours, or quarter, or hours, then you can have days, month, or week, and so on. Yes. It is necessary to define the dimensions and to define the granularity and the levels of dimension, and it depends on the analysis. So, I said that the methodology was defined into two parts. So, first, to define the generic model, and then to define the language and the tool to allow to the scientists, which are not computer scientists, to explore and to have an interactive approach of the exploration of the data, so to make them analyze the data. So, for this, it is necessary, again, multidisciplinary meetings, and again to understand what each people want to understand. And then to co-construct a methodology for data exploration. This methodology must be iterative and incremental. Incremental is for scientists because they analyze the data and they say, oh, I see something that is it's amazing. Oh, I want to go deeper for this. So I want to come back and I change some parameters and I analyze. So it is necessary for them to be incremental and to have new parameters and to allow to have new parameters in the methodology of analysis. So the targets are try to define multidimensional series of data. When you have a lot of data, now for each data you want to have a multidimensional. So it became a bit complex. We want to do multi-dimension aggregations operations. Because when you have dimensions, for example, timestamp, minute, hours, days, week, month, years, when at each step, each level, you have to aggregate the data. And the challenge is to homogenize visualization to highlight correlation. When you want to merge data coming from surveys, answer to questions, and measures coming from physical sensors on the same visualization. So, first step, modeling. we do? Well, how was with our work? From you see this from 10 years ago. The first model of sensor was created, and then every year or more, 4 models for in 2007. There were a lot of sensor models because the research concerning the sensors is about the start about 10 years ago. And all these models have focus on different things. Some models the sensors, the network of the sensors, the communication between the sensor, the efficiency of the network of the sensor. Some of them focus on the observation. This is for biologists for this model. And they focus on various things. And there is no generic model for physical sensor. But in 2012, there was the SSN model. It is an ontology which became a standard, but is focused on sensors. And it describes and have a specific concept for network of sensors. I come back after to define more precisely SSN. So a lot of models concerning physical sensors. I was working before on a model for the sensor data for environmental risk and for volcanoes. And I had more than 10 years ago some works concerning data modeling. So using these models, this knowledge, and all the work made on sensor, we define our own sensor model that we call M1. And then we try to analyze what are survey, and is there a model for survey, data model for survey? We didn't find data survey. So we analyze survey tools, because there are a lot of survey tools, and try to make a retro engineering of a model to understand what are the concepts in data model for survey tools. And we made a survey model, M2, talking with social people. And then we made an alignment between this model using SSN, which is standard, and try to design a generic model, virtual generic sensor model, which can be used to manage data coming from sensor and data coming from surveys. And then this concept model can have a life cycle of computer science project, and we have a logical model and then a physical model and manage real data and use this data to analyze and visualize and so on. So just have a look on a part of SSN. You see there, the focus is made on sensor. You have the sensor has sensing device, the sensor has sensor output, and sensor output data. Very, very simple. So we are interested in data. And we think that data is more complex than what they say about here. Here you have the device, the system, concerning the process, input-output, and the deployment of the process. So this sensor have measurement capability, conditions, each sensor have property, and so on. So the concept defined by the sensor ontology SSN, we use this concept, but we are going to have a focus on this part and to detail this part. So our first model, sensor data model, so the center is sensor and data. It's not sensor, but it's sensor and data coming from sensor. So we have sensor. This sensor has a location, has property. Each sensor has a lot of probe or detector. In French, we say sonde. A probe can measure some measures and have a measure type, temperature. One probe, one temperature or luminosity or and so on. The measure can be in a measure set. Measure sets are made for campaign, and the campaign are made for observation of energy efficiency, of pollution, of the mind, and concern an observation area. So this is a type of model to analyze sensor data, and the data are here. So I present you the first model. So then we focus on the second model concerning survey to understand the concept which are managed by the survey and the social scientists. The social scientists use surveys, use tools for surveys, but they don't care of the data model. And we try to find conceptual model published, and we didn't find. So we analyze existing tools like Lime survey, Sphinx, spreadsheet, and for example, you have the Lime survey database. So to understand what are the concepts managed by the users. And when we did this, we were talking with the social scientists. They used to not use this type. They use Excel. Excel, because it's common. Everybody knows Excel. So first we say, maybe there are tools. Oh, Excel. All right. So we have in mind these tools, and so the behaviors are not this. So with Excel, it's more difficult to have a database. So we were very interested in the Lime survey database to understand the concept that social scientists manage, but they have it's difficult for them to say that they manage this concept. So to make the concept emerging, the use of the Lime survey model was very useful. So then, with the social scientists, we designed this model. So they work by defining a questionnaire. The questionnaire is made with a group of questions. Each group of questions contains questions. The questions can be composed or can be with a simple question. So the question can be composed of a lot of simple questions. And the question can have attributes, and when the question is asked to people, there is an answer to the question. The set of answers constitutes the copy. A copy is for one people you ask the question concerning all the questions of the questionnaire. Each answer can have values. These values can be predefined or not. And at the left, then the questionnaire concern a survey. The survey can have multiple campaigns, and the campaign concerns an observation area. And in the campaign, you have a lot of investigators which have to talk to the people and ask the question and to fill the copies to the question. So having this model, it was to this type of model, it's a UML model. UML is very useful for computer scientists. When you have this model and you are working with social scientists, you need time to make them understand the concept, the relation, what we are doing this, and so on. So to obtain this one, it's not 1 hour, we are together, we speak, and this model appears. No, we need a lot of hours to discuss, to understand, to explain our methodology, to explain our type of model, to explain UML and why we are doing this. So now we have the model M1 and we have the model M2. Why? To understand each people, each discipline. And we have the same vocabulary for the survey model M2 with the social scientist, and for the sensor model with the thermal scientist. They agree with our approach and our model. And then we say we want to have a generic model. Why? To manage data coming from survey, coming from sensor, and try to have the same concepts to manage this type of data. So we call this model VGS model, virtual generic sensor. In this model, we will have two parts. The static parts, describing the system, and the dynamic parts with the real-time data and timing data, which depends on time. So we use the concept of hypothesis, which is used in the standard. The hypothesis is the object of study, what we want to study. Energy efficiency, pollution. One sensor has multiple detectors. So one sensor can measure various data, temperature, luminosity, and so on. Or one sensor can measure only one type of measure. But the measure is made by the detector, and a sensor can have many detectors. A detector has one measure type, and a measure type has several measure attributes. The dynamic part concerns the collected data. You have a deployment, it's between a date to a date, and you have a deployment to make a campaign. A deployment is a campaign of measurement. Then, in real time, there are a lot of measures we are made with the network of the sensors, and the sensor produces sample of measures, sample set of measures. And then a measures is a set of values. A measure is a set of values. It's not a values, it's a set of values. So now you have the concept, and this is the model. And it's up to Yann. We change.
Right. I'm going to go on with the model. So like Sylvie said, so we've got hypothesis, deployment, the static part here, organized with sensor having detector, one measure type described by different measure attributes. This part, you may think it's a lot of things for sensors, but for physical sensor, you can say, okay, it's one temperature sensor. Why there is a detector, measure type, measure attributes? But while discussing with thermal scientists and, which is a very interesting point, with social scientists, with survey, we found that it's necessary to describe, to further describe what is a sensor, what is a detector, to structure data, and then to make easier data analysis. If we stay fuzzy about data, it's very difficult to make analysis, to make query on data. If we structure data very precisely, then it's more easy, it's easier to query, to aggregate data. So that's why we describe the structure of data, and here we've got values of, we've got a dynamic part, the data produced by the system. One measure, if it's a detector that has several attributes, for example, a GPS detector, you can see it as a detector which produces 3 values, the X, Y, Z of the location. So then you can have 3 measure attributes, and here 3 values for each measure. So one example on this model in our smart building platform. So it's just a slide from before. So we had 300 sensors. We had a variety of sensors, and to describe this platform, our model was very helpful to easily manage data coming from those heterogeneous sensors. It was all physical sensors the first time, but to make the distinction between temperature, CO2, opening of door and windows, our model was already helpful. Then to integrate user survey, like we will see in the example, it was mandatory to have this precise model to manage homogeneously those heterogeneous data. So in our platform, we had here in the example, we focus on temperature measurements. So we've got physical sensor, like this one, for example. So with a lot of temperature measures, it's for about 3 years, no? About 3 years of data. And one survey concerning occupants' feeling, with was one questionnaire and about 10 questions asked to user. So with this heterogeneous data, how to represent them in our generic model. So here still the model in UML. For the physical temperature sensor, so the physical device, the electronic device that you can put somewhere in your building, it's the sensor concept. The physical, the sensible part that makes the acquisition of the measure, the physical measure, is the detector, what we can call also a probe, a physical probe. So you've got one temperature sensor, a device, one detector that can measure the physical device, so which thermocouple is one technology of temperature detector. And in this simple case, we have only one measure attribute, which is temperature. We could have several temperature attributes if the detector is more complex. So here for physical sensor, and if we integrate survey data, so on the static part that describe the system that allow to capture data, we have a parallel. When we have an electronic device, the temperature sensor, we have a questionnaire. When we have one physical detector, you have one question. And when you have one measure attributes, physical attributes temperature, you have the type of answers to the question. And it allows to structure data that will be produced by this system. Physical device, here temperature, and social process, social surveys with the questionnaire. On the dynamic part, we have the same parallel concepts. We've got a sample which is data produced by a device at a certain time. This sample can be composed of several measures. For example, you have a device that measures at the window, on the wall, and so on. And these measures have values depending on the attribute. Here, just one temperature attribute, so one value, which is the temperature. And with the social survey, you have the parallel concepts, which is the sample corresponds to the field copy at a certain time, which is all the answers to questions composed of values. Here, in this copy, this sample, we've got one answer to question 2, and this answer is -3. So we put heterogeneous data in a homogeneous generic model, a part that describe the system, describe the physical sensor, describe questionnaires, and a dynamic part where we put the data produced by this system, by this different system. And the goal to manage homogeneously those data is to provide common language and tools to explore, to interactively explore those data. You have data coming from different systems, but then when it's in this generic model, you can analyze, you can explore those data independently from the different systems that produced them. So, like Sylvie said before, so we had a lot of discussion, and the goal is to have this concept of multidimensional series of data coming from the generic model to define multidimensional aggregation operations, to build interesting data, and then we define some way to visualize those data. So on our VGS model, we implemented in a database. We had a VGS database, and we provided to users, to managers, tools to for first step to see, to watch their data. So here we can see a simple dashboard with some graphs here, some tables, which simply display data. But what you can see, you can't see very well, but what you can see here is data coming from the VGS database. So it can be temperature data, but it can also be answers to surveys. Data here comes from queries on the VGS model. So we have integrated data into a VGS model, to the VGS database here, and then these tools can work for both data. So you can homogeneously visualize raw data from survey or physical sensors. We also built a nicer interface. So here it's one stair of a building, of our building, and we display sensor data, sensor information on a 3D model of our building. It's another kind of visualization, and in each room here we can have different information. For example, here the color corresponds to the average temperatures, and we can have also some small labels where we can provide numbers or textual information on each room. So it's different interfaces which can display raw data from heterogeneous systems. What we want is to go further. So here just to display data, to visualize data. Now we want to analyze those data. So it's what we propose then. And to analyze data, like Sylvie said before, we want to benefit from their multidimensional property. Data, sensor data, and generic sensor data can be described by several dimensions: time, locations, and source, what produced the data. And we want users to define their own dimensions, and it's a work in progress, but we are building a tools to allow users to easily define how do they see the time, what levels of granularity they want for explorations. Do they want by minutes, by day, by week, and so on? And these dimensions, so it's for time or location also, rooms, the stairs, and so on. For the source also, so you've got detectors, you've got samples, which are part or produced by a sensor, and so on. So these different levels will allow to, at first step, aggregate data. For example, if you want an average by day or an average by hour, and the composition of aggregation, like we will see. And then we will use also these dimensions to explore data, not only to aggregate data, to calculate average values, but also to define what data we want to visualize. So we will see here the first step, which is the aggregation of data. So what we want to do is to provide user with tools, with language to define precisely how to aggregate data. So we have on the first line here, you've got the raw data. On each dimension, we have at the base level, got the timestamp, the precise location, and the measure source. It's the smallest grain, which is a value is part of a measure. We've got two multidimensional series here because we've got temperature series and feeling series. It comes from different systems, survey and physical, but here now it's values from multidimensional series because they are in the virtual generic sensor model. We can see them as values in a multidimensional series. And on those data, we can apply aggregations. So, for example, temperature, we've got the raw data. We want here to have an average by hour, by room, whatever the source. We define a new indicator, which is, let's call it room temperatures, which is an average temperature by hour, by room. We can define precisely this aggregation. And then the scientist can say, what is interesting for me is building on this room temperature, to construct on this room temperature indicator, another indicator, which is by day, by building, whatever the source, I want the max temperature, the average temperature, and the minimum temperature. And the scientist can build the precise information he wants by defining aggregation steps. And on another multidimensional series, the feeling, he or she can define just, for example, one aggregation step, which means here, by day and by building, I just want the average feeling of users. So we benefit from the dimensions to define aggregation steps Yes, there is a summary here. So from our dimensions from before, where we had time, location, and source, the user can say, to define the room temperature, I want the average, and I go by hour, by building, and whatever the source. Here it's all sources. And one step again to say it's by day, by building, and whatever the source. So we can visually define some aggregation and to go up in the dimensions for one series, for the other one. So he builds indicators, here the max temp, average temp, min temp, and average filling at these levels. The next step then is to visualize those indicators. And still with the dimensions, what we want to produce, or what we want the user to be able to define is, I've got an indicator which is by day, but I want to see it by month. I want all the day of the month. Here, the data is aggregated at the building granularity, and the user say, okay, I stay at the building granularity. And the source, it was whatever the source. And just by defining this level of visualization, which is not a data aggregation, but at which level you want to visualize your data, the system can produce a graph like this one, where we have the temperatures, we've got the max, the average, the mean, and we've got the filling indicator, which was the average filling, here with the green bars, and for all day of the month. So the user has defined on the dimension, using the dimensions, how to aggregate data to build the indicators he is interested in, and to define the visualization that he wants to see, to analyze data. And here he can focus on what is the correlation between the fillings, the average filling, because it's what he's interested in, and the max or average or mean temperatures in the building. So data are integrated into the VGS model. We define dimensions, the user defined dimensions, and then aggregation steps and visualization steps. And to go further, again, here we have one graph. If we want to provide the user with a multi-graph, where he will be able to compare visual indicators, different type of graph. For example, here we've got temperatures and humidity, and one graph for different for different members of the levels. For example, here for different rooms in the building. So what you see here, which can be defined still using the dimensions, it's a bit more complex, but you have for the temperature on the left in the red graph, it's average temperature by hour by sensor. But you visualize it for 1 month and by room. So here you've got several sensors, several temperature detector in the room. So you've got several lines, and you see the evolution for all the day of the month. In the next one, in this room, you have only one sensor, for example, and also in this one. And so you can compare between rooms, and you see different sensors in the room. Just by defining here that data is aggregated by detectors, but when you visualize, so by detectors, room and hour, so data is aggregated, you've got one values by hour, by room, by detector, when you visualize it, you want in one case, in one cell here, you want it by room, by month, and whatever the source. So you've got all the detectors, one line by detectors, and here you've got all the rooms of the building, and all the day of the, and here all the day of the month. So just by interacting with the dimension, the user can define aggregation, aggregated indicators, and then visualizations by projecting those values among dimensions, among time, source, and location. And you can then make a visual correlation also between different indicators, and you can add with the incremental methodology, you can add new indicators to say, okay, there is something strange here. I need a new indicator. I put it next to one and say, okay, this is strange here, but I can explain it with this other indicator.
So we present our approach to try to manage heterogeneous data, and this heterogeneous data to have more homogeneous models, and then to define exploration to help scientists to understand data and to understand phenomena. So the most important is to, one of the most important things is to merge approach coming from various disciplines. Then the second important thing is that we manage heterogeneous data with an homogeneous approach. So it's a kind of integration approach, but we made this by concepts, and then we managed to have physical management and to have physical databases that can be used and then analyzed, and then to have homogeneous analyzing of various data, and this various analysis can be made by social scientists or by thermal scientists, and with the same approach, the integrated approach. So we designed a generic model, which can be it's more usual to say generic ontologies, but for us, we come from the database, we are database scientists, so for us it's models, because we use this in tools. And we define a language for multidimensional analysis, a language with dimension to design aggregation, and dimension to design visualizations. And it is the same. You use the same to aggregate and to visualize, and it's important for not computering scientists. So we have a language for multidimensional analysis and for visual exploration analysis indicators. And this methodology is agile because the scientist, it's not like you have a lot of tools like data warehouse tools. It's for businessmen. You know what you want to see, you know what are the indicators, and it's only the same indicators for business. It's quite the same, but not the same for scientists, because they want to explore, they want to understand, and then they want to increment the analysis and to add some indicators, to add some analyze, to add some level in dimensions, to add dimensions, and it's a process. It's not like for business, and you see indicators, and it's always the same indicators. So the methodology must be incremental, so it is necessary to be agile, and so to offer to the user to add information, to add level, to add indicators. And it's not so easy. It's iterative because you can use some results, data result, because you can use aggregated data, and you can have this aggregate data. I want to confront with raw data, and we want to allow this. And it is interactive because to allow definitions of new indicators, to allow to visual navigation, and to allow also to store analysis, to store results, because it's necessary for scientists to play again the scenarios. And we have this in mind, to have some analysis, to store results, and to be able to replay all the scenario to better understand and to confront the process of analysis and why we add indicators and why we do this and why we do this, and to replay. It's very important to understand. We finished.
Thank you very much. So there's room for questions. I have also questions here online.
Can I ask?
Yes.
Thank you very much for a very interesting talk. And actually, we are developing the same kind of system in Japan, and which we get the sensor data like the temperature, humidity, from heterogeneous sensors. So I feel it's very important to have this kind of reference model standard, which standardize the structure of the sensor data. And my question is that how do you manage the heterogeneity of the meaning of the data itself? So, for example, for the temperature value can be represented by the Celsius in US and in Fahrenheit in US. To represent the same thing, there are two different representations. Also to represent the time in Japan, it's 9 hours before. So if you have the same, if you have different values, it can be the same meaning. So you have to align this kind of, how to say, it's very difficult to say.
Is your question concerned, for example, it's the measure of the temperature, the value of the unity of measures? So difference in USA it's Fahrenheit and all that.
So if you aggregate two of them, you have to make a kind of a conversion to say, you have to standardize.
But yeah, it's the part of the things we want to describe in the description of the system. Each detector can have its own unit of measure.
Okay.
And we want to store it, to represent it, to say that this value, its numeric value, is linked to some measure attributes that describe what is this value.
So this is not here. This is here. Unit.
Okay. Unit.
Yeah.
So unit attribute.
You have only a value. It's a value. It can be a number. It can be a word. It's a value.
Okay.
And the unit of the value is described here.
So
it's very important to separate.
Yes.
Yeah. And it's up for the user then to understand that this value is with this unit, and you can compare one unit to another unit.
Okay. So if you have two different data sources from US and Europe, then you have to add kind of conversion.
Yeah. If you want to compare temperature and with various units, you need to have a system to compare this. But we know that it's possible, so it's not a problem for us.
Okay, so you have this kind of
the important for us is to have the concepts and the granularity of the concept. We know that with system of transcription and so on, we can do it. But it's why we describe the unit, it's not the same concept than the value.
And we have the same problem, in fact, with temperature sensor from one instrumentation. It's not a building, it's an experimental setting, where in fact temperature is measured as a voltage. So in raw data, the temperature sensor, in fact, we have a value of voltage. So we represent it to say this measure type has several attributes, one voltage and one temperature. And we store the voltage, and we have post-processing to compute this value with, for example, a unit Celsius. That will be the same thing, in fact. We have some raw value which are from the system, which have different units. And you can do some post-processing to say, okay, we've got one attribute which is the raw value in some unit, and another one which is another attribute which is the value converted in your unit you want to use in your analysis.
Because we have a second use case, it's with thermal scientists to better understand the use of photovoltaic panels. That's photovoltaic panel. Yeah. To better understand, because sometimes there are problems that they don't understand, and it's necessary for them to have a lot of information from the wind, the sun, and les ruissellements, the water. There is water on the panels and so on, and it's difficult to understand why the panels are not so efficient as they ought to be. So we have a second. And in this type of experimentation, we have a lot of physical sensor, but they are very, very different. It's not with the surveys and so on, but a lot of sensor very different on granularity of data, on unit, and so on.
My question is, you said that you have different types of sensors, right? So you need to structure the data before applying the model, or how do you do? Because if are different, the type of data is different, the output are different. So you need to structure the data, or you use the data how they can you apply it.
It's when to do the integration into this model, in fact. When? it depends, if I understand correctly, it depends on your settings. For smart building experimentation, we developed our software sensor gateway. So data was the extracting from raw sensor data already into this model. So we had a VGS databases behind. But you can also see the VGS model as a model for data integration, where you have your database or files and so on, and you see this model just like a view on your data. Both are possible, in fact.
Yeah.
Hi, do you take into account for future work? Because I haven't seen it in the models quality attributes, like it's available, the sensor is available, it's reliable.
No.
Something like that.
Not at all.
No?
Not at all. Because of quality. I love quality, but we don't have enough time to do all the things. But the next step is to take into account quality. But the first was to integrate information, to try to do science analysis and with heterogeneous data. Then the next step is to see if, concerning data quality, when you have this, I have a lot of discussions with Christine about data quality because a lot of scientists need full data and good data. Good data is that data must be have the value between this and this. Oh, we have a lack of data, so we fulfill. We don't want, because if there is a lack of data, we think that for the scientists who analyze, it may be an information. This, like the sensor is out, or there is a problem concerning photovoltaic panels, but there was the wind, or there was a rain, or and so on. So we think that sometimes it depends on what you are going to analyze, but sometimes the fact not to have data quality and to have the raw data is important. And then when you analyze the data, you can see, poof, oh, there is a problem. What? We want to go deeper. If you have average data, it's not the same. You need for some analyze, you need to have data, not lack of data, all the data are fulfilled and so on, but it depends on the analysis you want to do. And sometimes to have the raw data and to analyze the raw data, this type of analysis is possible. Our tools can see the data who is not good or there is a problem, and this problem has a signification, may have a signification for the analysis. So we don't want to, we can have a lack of data, and this lack of data can be useful for the analysis. It's not the same when you want to have tools or a system who have to calculate a lot of indicators, and if you have a lack of data, these indicators can't be calculated. It's not the same process here. So it is data quality is important, but to correct data, sometimes it is not useful. Is it clear?
Yeah, no, because it was the context you say it makes sense. I'm saying about making queries on sensors that are more reliable than others. That they have precise data, and so in queries you can discard unusual sensors.
Yes, but imprecise data or lack of data
in
can be
context, it's important.
Yeah. And with a lot of type of visualization, you can point this type of data and to try to understand why, or it is imprecise, why. And sometimes it's important because it's an emergence of a phenomena that you want to understand.
So another point, because like you have several measure attributes by sensors, you can think of adding some quality measure attributes to sensor to visualize those indicators next to data in the VGS model. It's not integrated as quality, but you could think of adding some attributes that represents quality to visualize them like other data.
There are two questions. My question is about how the scientist interacts with the system. He defines drawings like that or workflows. How he does this?
Je fais ça à la fin, non, là peut-être. Non, on n'a pas le.
How he defines the indicators and stuff. How is the interaction with it?
It was it is in fact still the multidisciplinary meetings. We have a lot of meetings to understand their process and so on, and to define, for example, dimensions. It's a work in progress to define precisely what are the dimensions we're interested in. For example, time is not easy to understand because we have.
Now you have the system.
Yeah.
And how the scientists use the system.
Yeah.
How he makes an analysis. It's more like this.
It's the tools we are finalizing. Let's say now they will be able, they will have those drawing of dimensions. They will be able to click on different levels and define aggregation. To define something like that, to say, okay, I want to go to levels hour, room, all, and to define room temperature as average of temperature. They will,
they define. They click on this. They click, and then they click. You have in a window, you can have remplir des chantiers là. Des chantiers, and they can enter what they want to see.
Okay. Just one more question. What type of database do you use to store all the data?
So for example, it's SQL or MySQL database, and we are studying also NoSQL databases like MongoDB and HBase. We have a postdoc colleague that is studying, but it's also a question of optimization and efficiency. So we are finalizing our prototype, and we will compare, in fact, different storage way in different databases to see what
databases, data warehouse, and so on.
The number of sensors and servers.
And we want to have a web configuration, so it's not so easy.
Thank you.
At the beginning of the talk, you mentioned that you were interested in the language to do aggregations. What kind of language have you managed to produce?
It's an algebra. So we extended the relational algebra.
Like SQL?
Yeah. We mixed, in fact, relational algebra and a model of dimensions to add new operators, to have some like cube operators to define aggregation. We go from those levels to those levels, and we define indicators like a function on. We define indicators at one level, depending on indicators at the levels below. So it's like an algebra. There are some algebra, some
existing
cube or data warehouse algebra in the related work, so it's similar, in fact. But we have some points that we need to see with thermal scientists and social scientists who say there is something they want to express that is not easy with related with state-of-the-art algebra that we want to include in our algebra. So, but end users will not see the algebra, but it will be behind the scene. So it will be here. Yes. In fact, the table. This table, in fact, is a simple representation of here two aggregation operators applied on the
based
data.
on the fact table, like in the tables approach.
And another question is, what kind of streaming you have? You're not worried about streaming.
Yeah. Yeah, because streaming, because for us, the goal, the target is to help scientists to understand. It's not we don't focus on the real-time aspect in this type of program. I worked before on the real-time aspect and from the optimization of data and time and so on. But in this type of program, it's not the real-time the focus. It's to understand the complexity of lot of data. So we can say that it will be it could be a next step to say that we have the real-time and we have a real-time analysis, but it's not our focus in this type of problem. But we have stream because the data come from our sensors, and we have the stream, and Jan worked before in his PhD thesis. He works on the system to have a continuous way to queries and on the stream. But we use this to acquire the data, to collect the data, and the focus now is to analyze very heterogeneous data, and not real time is not important here.
I have 4 questions online.
Mm-hmm.
I will try to sum up some of them. So there's one related with the model. It says, your strategy makes us think about multidimensional models on data warehouses. What is similar about those approaches and yours? So that's one. The other has to do with the modeling of dynamic aspects. So they say, we understand you are modeling a static aspect of the problem. How can the dynamic aspect of data production be integrated in your model?
So it will, I think it will be about the same answer. In fact,
yes.
what we don't want to do is a static data warehouse, because data are like streaming data, or database is filling continuously. So we don't want to say at one moment, okay, we take data, we build data warehouse to have some visualization. We want it to be more streamlined.
Acquisition and the data is collected in the database, but it's continuously. Yeah.
And it's where our model is very important, because the integration of data is more to VGS model part, and then the definition of indicators and so on is independent from the data that is from data acquisition. So we define what we want to do, aggregation levels and visualization on the VGS model, and there is the question of data that is filling, but it's separated.
So there's another one. Did you adopt a specific strategy for making decisions on where and how much sensors you installed in the building?
The first, sorry, the first part of the question.
Did you adopt a specific strategy on where and how much sensors you installed in the building?
So yeah, it's with a thermal scientist, in fact. So it is a multidisciplinary team. So it was thermal scientists that say it will be interested to have sensors here, 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 and here. So it was the joint work with other disciplines.
And the last one is, how did you model urban phenomena?
Our model doesn't depend on urban phenomena. It can be used to analyze urban phenomena, but the model is not for urban phenomena. It is a model for data and to manage a lot of data which are very different and which are very heterogeneous. But we can use this model to analyze health problems, for example. The concepts are very generic, but it is necessary then for health. If I imagine what is a sensor, if it is not a physical sensor, what can be a sensor? Like for us, for surveys, a sensor is a questionnaire. So you have to have a first step of analysis to understand what is a sensor, because it's our pivot concept, the detector, the measure type, and so on. To have an alignment, a matching between existing concept, and to say, well, sensor is this, but we think that these concepts can be a pivot for a lot of concepts.
In fact, we model not the phenomena, but the observation of the phenomena with generic sensors.
Well, thank you very much for your attention. Thank you very much for your information. We have 3 groups of people connected. So there were 2 from Mexico and 1 from Paraná. The questions.
C'est tôt pour eux, non?
Yes, they're early.
It's early for them.
Yes. Maybe they're listening you in bed. Thank you very much. So,
Thank you.
Our next, now it's time for lunch. In the site, you can find suggestions for those restaurants that you can go for lunch. And then we are starting again. I want to see the program, otherwise at 2 o'clock.
On était bien.
If you want
mais on a
to
commencé
leave
plus tard.
your things here, you can. I want to close the group.
International,